Hi, everyone. So welcome to week 7 of this semester. This week's lab briefing, I want to start off with a quick review of what we've seen so far. So basically, in the first 5 weeks, we've looked at some of the basic skills that you will need to measure currents and voltages and other signals in the lab, and including DC as well as AC signals. And in the fifth lab, we also learned a little bit about some of the circuit analysis tools, plus did some um, circuit building involving more than two resistors. Right. So I'm just gonna go do a quick review of the skills that you should have learned so far in the first 5 weeks of the lab, and because starting lab 7, we're just going to do different circuits and look at different circuit phenomena, but you'll be using the same set of skills that you've learned so far. Okay. So first of all, you learned about measuring DC voltage and currents. Okay. Using a DMM. Now, the key here was to, whenever measuring a voltage, to attach the voltmeter in parallel to the voltage that you're trying to measure. Whereas when you're trying to measure a current, you want it to be the ammeter to be attached in series uh, with the current that you're trying to measure. Okay, so you want the current to be um, the same current to go through the dot as the ammeter, whereas for the voltmeter case, you want the same voltage across the dot and the voltmeter. We learned how to generate AC signals with a wavegen. So this is generate, and to measure AC signals with an oscilloscope. And on an 82, these wavegen pins correspond to pins W1 and W2, and the oscilloscope pins correspond to channel 1 plus and channel 2 1 minus, making one set of channel, and channel 2 plus and channel 2 minus. Okay. You learned how to adjust scales and offsets on the oscilloscope to be able to visualize the circuit, different aspects of the circuit. Okay. Fourth, you learned how to trigger um, the signals using, say, hold off sometimes, with or without hold off, and also with a synchronous signal that's being generated. Okay, so hold off is, well, first of all, triggering is the idea of instructing the oscilloscope to refresh the image every so often so that uh, the 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 signal that's resolved on the display is humanly viewable. Or the other use is to visualize some transient property of the signal that may get missed without a proper triggering. Right? And hold off is a setting in the oscilloscope that which tells it to, well, hold off or to wait certain period of time between trigger events. And sync is a synchronous signal a wave generator will generate, or you can make the wave generate to be synchronous to all of the other signals being generated, right? And the beauty of the sync signal is that if you trigger the oscilloscope on a sync signal, then all of the signals that's being generated by a function generator is automatically synchronized to it and is properly triggered when viewing on the oscilloscope. Okay, so those are the key measurement techniques, circuit measurement techniques that you've learned so far. Besides these, you've also learned circuit analysis tools. I guess the very first one being Ohm's law, V equals IR. Um, this is the current voltage relationship of a resistor. You've learned about equivalent circuits, right? And what equivalent circuits tell is that um, a larger circuit with lots and lots of components, its behavior can be modeled using a much smaller circuit um, containing, say, only a voltage source and a series resistance, right? And that's a Thevenin equivalent model circuit. And also, you can model it with a simple current and a parallel resistance, which would be the Norton equivalent circuit. You learned about how to measure these Thevenin and Norton parameters, um, and you applied those skills in Lab 5 as well as in the lab practical. You also learned about, um, well, in doing equivalent circuits, you learned about parallel and series resistance and how they add, or actually you learned about it before also. So you learned about how to calculate the combinations of series resistances and parallel resistances. Um, the fourth thing would be superposition. And this basically tells you that if you have multiple inputs in a circuit, the behavior of the circuit due to the combination of sources is same as the sum of the behavior of the circuit due to each of those sources applied individually. Okay, so these two are quite powerful circuit analysis tools, and you'll need to use them moving forward in the course. Okay, so that's a quick review. And just as a quick comment, majority of the class did exceedingly well on the lab practical. I think 50 to 55% of the class got above 90, so that's a really good job. Congratulations on that. And yeah, so that's a quick review of what we've done so far in this course. Okay, so now for this week's lab, what we're going to talk about is inductors and capacitors. Okay, so inductors and capacitors are another kind of devices, circuit elements that you construct circuits out of, like resistors. However, they differ from resistors um, in a very key and important way, right? So resistors are dissipative elements. So when you apply a voltage or current through it, then it dissipates power to the environment and you lose power, right? Whereas capacitors and inductors are really energy storage devices. So when there's a voltage applied across it, you don't actually lose any power. You simply um, accumulate energy on the inductor or the capacitor. Okay. So, but what really are inductors and capacitors? Right? So, so in general, a capacitor is, when we talk about a capacitor, we generally think of parallel plate capacitors. It's basically two metal sheets separated by some non-conducting material. And Yeah, so the idea here is that when you apply, when you run some, try and run some current through the capacitor, there's actually, you can't directly run current through it, right? Because there's a gap in between. But what ends up happening is you start accumulating charge on one of the plates, and on the other plate, you start repelling positive charges. And what that means is that you start accumulating negative charges, right? So you start accumulating these positive and negative charges on the two plates of the capacitor. And what that does is that gives rise to some finite voltage across the two plates, right? So this is electrical potential energy. Because of the accumulation of charge, there is some force of attraction between the charges, and so that gives rise to some potential energy. Okay, so this is how a capacitor stores electrical potential energy. Okay. Similarly, an inductor, when we think of an inductor, is a wire coiled around some magnetic material. Okay. And in this case, what happens is when you run a current through the inductor, it will go through it quite well. But here's the thing. So it's basically a piece of wire. So it has zero resistance. But still, what can happen is as you run the current through it, you will generate some magnetic flux on it, around it. And due to the changing magnetic flux, you will create some voltage, some finite voltage across it, right? So there will be some finite voltage created between uh, uh, the two ends of the inductor, even though it's just a piece of wire. Okay, and so the inductor stores energy in its magnetic flux as magnetic potential energy. Okay, so magnetic flux, let's call it phi b. Okay, so you'll learn more about the internals of the capacitor and the inductor more in detail in probably some other courses or in maybe some physics courses. But what we're more concerned about here is how the quantities here are related, the voltage and the charge, and the current through the inductor and the magnetic flux or its voltage as well. Right, so let's start with the capacitor. So what governs how much voltage is created given the charge accumulation is basically, first of all, it depends on what kind of materials separates these two charges, the dielectric. How big is this distance between the two plates and how big the plates themselves are, right? So these are all questions about geometry and materials. But like I said, like a parallel plate capacitor is only an example. You can have a capacitor that's cylindrical and shaped like this, right? So you can have a capacitor whose first plate is the outer shell and the second plate is the inner shell. It's similar to a coaxial cable, right? So geometry, materials, size, everything plays into how much voltage is created. But all of that physics um, uh, can be and is usually captured in one constant called the capacitance of a capacitor. And that basically says in one value capacitance. And that basically means, what it basically means is that Q equals CV, okay? So it says that for every 1 coulomb of charge um, accumulated on the uh, plates, you will get C volts of voltage appear across the two charges, two plates. Similarly, um, for the inductor case, the question about how much current is needed to create a unit flux around the inductor, magnetic flux around the inductor, is given by uh, uh, inductance L. Okay, so again, this L in the inductance value captures all sorts of phenomena and geometry and material parameters, but this inductance value is what we're mostly concerned about. Okay, so in the lab, pre-lab, you will do an exercise of actually calculating the inductance for a wire coil around some magnetic material, and use properties of geometry and material parameters to calculate it. Okay, but you should just be aware of this. Okay, but okay, so we've got a relation between charge and voltage here, and for an inductor, magnetic flux and current. But so far we've only been dealing with currents and voltages. Okay, resistors was described by a relation between a current and voltage. Like I mentioned before, all devices are generally described by their current voltage relationship. So let's get a relationship between current and voltages for these capacitors and inductors as well. What you can do is starting from this constitutive relationship, if you take the first derivative with respect to time, then what you get on the left-hand side here is rate of change of charge, and that is basically current. And so what you end up with is I going through the capacitor is C times the d dt of the capacitor voltage. Similarly here, you take this first derivative with respect to time, and what you'll get is, now this might not be very obvious, but the rate of change of magnetic flux will give you the voltage across the inductor. This is something you'll learn in some electromagnetics course, and you'll end up with L di dt. Okay, so we've gotten the IV relationship of a capacitor, but now you see that these are actually differential equations. They're differentially related rather than simple linear relation like that of a resistor. Okay. Okay, the circuit symbol for a capacitor is, it looks like two parallel plates. Sometimes some capacitors are also drawn with a curved plate. These are special capacitors, and we'll talk about them later. An inductor is shown is represented by this squiggly line, sort of mimicking the coils of the inductor. Okay, finally, the units of capacitance. Capacitance is measured in units of farad, in short F, and the typical ranges for capacitances run from nanofarads to millifarads. Okay, the units for inductance L is Henry, and is shortened to H, and the typical range for inductances is from microhenries up to millihenries. Okay, you can have wider ranges of both of these values, but these are typical lab values that for discrete elements. Okay, so now the next natural question is, how do you measure the capacitance or inductance value of a capacitor and an inductor? Right, and the answer is there are instruments that do it, and we have those in the lab. They're called LCR meters. Basically stands for inductance capacitor resistance meters, and they make measurements on for all three quantities. Okay, but there are other circuit techniques to measure capacitance and inductances as well, and that's using some calibrated test circuit. What that basically means is that you have a circuit with all known components, and you just stick in a capacitor in there and look at the behavior of that circuit. Depending on the value of the capacitance, the behavior of the circuit, or the signals that you measure on that circuit, will be of a certain type, or of certain amplitude and phase and everything, right? So that's calibrated test technique. And that's what we're going to do in task 1 and task 2 of this lab, is to use a calibrated test circuit to estimate the values of capacitances and inductances. Okay, So yes, so task 1 and task 2, you're gonna estimate the capacitance. Task 1, you're gonna do capacitance, and task 2, you're gonna do inductance using time domain measurements on a test circuit. And the test circuit has been given to you. It's in the lab manual, but this is the test circuit. Um, and how are we going to make this measurement, right? So there's a very good example in the lab manual, example 7.4.1, that goes through all of the details of making the measurements and calculating the values from the measurements. But the basic steps are: you measure the voltage across the capacitor, you measure the current through the capacitor, and then you use this current voltage relation of the capacitor to get back the value of capacitance. Okay, so you measure this and you measure this, and you calculate back whatever is remaining. Okay, so this test circuit consists of a sinusoidal voltage source and a sense resistor and a capacitor in series across the output of the voltage source. Okay, so one question sometimes folks get is what this RS is and whether that should be included in the circuit when you're building it. And the answer is no. This RS is a Thevenin resistance associated with the wavegen. So this is part of the source itself, and you have no control over it. So the only things that you're going to attach or build on your circuit is the R sense and the capacitor. Okay, so yeah, so I said that we're going to measure the capacitor voltage and the capacitor current, and those are the only two things we need to measure or estimate the capacitance back. Then why do we need this R sense, right? So that's the question: why do we need R sense? And the answer is to measure the capacitor current. As you know, you only know how to measure. We only have instruments that can measure DC currents with a DMM, but you never learn how to measure AC currents, right? So what we're going to do is we're going to measure instead the voltage across the resistor. And because the resistor and the capacitor are in series, uh, you can now use that voltage across the resistor as a measure for the current through the capacitor, right? So basically, mathematically, what I'm saying is IC, the current through the capacitor, equals the current through the resistor because they're in series. But IR, you can get from Ohm's law using V sense over R sense, right? So this is what I mean by a calibrated circuit, is that you know what are the value of R sense, right? So you know everything about the circuit except for the capacitance. Okay, so now using this relation for the capacitor voltage and current, and this relation that you just got between the capacitor current and the voltage sense voltage, you can construct this equation where you have all the known quantities except for the capacitance. Okay. Now, one quick note here is that Vsense and Vc, they're both time varying signals. So you're applying a sinusoidal voltage on the circuit. So what you measure, these voltages are also going to be sinusoidal. And when you express them and you're doing your math, you should also always express them as a sinusoidal voltage. Okay. Okay. And when deciding whether to call it a sine or a cosine, you can pick any arbitrary time position to be time equals 0 point. But just make it choose it such that it's easy to distinguish. It's one of the signals is easily a sine wave. Okay, so what I'm saying by that, if it's not very clear, is let's say this is what you saw on the oscilloscope. Okay, so the oscilloscope will have some arbitrary time equals 0 position depending on your trigger. but you don't have to pick that as your t equals 0 point. What you can do is, okay, so if I pick my time equals 0 right here, then this signal looks like a sine wave now, right? But if I had picked my t equals 0 to be point over here, this now looks like a cosine wave. Okay, so what I'm saying is there's going to be multiple signals here. So pick a time equals 0 point, and then based on that, one of the signals will be a sine wave, the other signal will be a cosine wave or a negative cosine or what have you, right? But stick to one t equals 0 point. That makes your life easy. Okay. So for more details on how to do the calculation and stuff, look at this example 7.4.1 in your lab manual. Okay, so how do you actually measure this stuff? Well, there's a picture in your lab manual which has different differential probes and everything labeled on this test circuit, but you don't need to worry about that. With the 82, what you're basically going to do is measure V-sense with one of the channels, and measure the capacitor voltage VC with another channel. Okay, and you're going to construct your circuit like this so that well, one of the nodes is a common node between the two, so it's going to get connected to both channels. Okay, so in reading the text in the lab manual, you'll come across this term called the DUT, DUT, which basically stands for device under test. So in this test circuit, the device under test is capacitor. They can use the same test circuit to measure an inductance, and you just say that the DUT is now an inductor instead of a capacitor, right? Okay, so in task one, you're going to estimate the capacitance of a 10 nanofarad capacitor. In second round, you're going to measure the capacitance of a series combination of two 10 nanofarad capacitors. Okay, and then next you're going to measure the capacitance of a parallel combination of two 10 nanofarad capacitors. So the DUT in each case is different. Okay. Now, to find the capacitance that you're looking for, the 10 nanofarad capacitor, well, the 10 nanofarad capacitor looks something like this in your kit. It should be a green looking capacitor and it has some numbering on it. Okay, so it should say something 103 something. Okay, so the important part about the capacitor value is in this three numbers. And similar to reading resistances, the first two digits give you the first two digits of the capacitor, whereas the third number gives you the multiplier. Okay, so 103 becomes 10 times 10 to the power 3 picofarads. Okay, so that's 1,000 picofarads, 10,000 picofarads, which is equal to 10 nanofarads. Okay, so if you had something that's at 475, that would be 47 times 10 to the power 5 picofarads, which would be 4.7 microfarads. Okay, so that's how capacitors are labeled, and that's how you can find them in your kit. Okay, in task two, you're going to do the same experiment, but use a 1 millihenry inductor instead. An inductor in your kit looks something like this, and it may, or it could also, some inductors also look like a blue cylinder with two leads, obviously. But regardless, it will have some labeling on it, either 102 like this, or it will directly say 1M, right, indicating 1 millihenry. So reading off the values from numbers like this is similar to the capacitor. It has got three numbers. The first two are the digits of the inductance, and the third is the multiplier. Now, in case of inductors, we express it in terms of microhenries. So 102 will be 10 times 10 to the power 2 microhenries, which is 1,000 microhenries, which is 1 millihenry. Okay. All right. So task 3, what we're going to do is, in this case, we're going to explore capacitive voltage dividers. So you've done resistive voltage dividers, put two resistors in series and measure the intermediate voltage. In this case, we're doing a capacitive voltage divider and seeing how it performs. Okay. Look at the text in the lab manual to see how capacitors combine when they're in series and how the capacitive voltage divider works in terms of math. Okay? But in this lab, what you're going to do is apply a sinusoidal voltage of certain frequency and look at the output and see how the amplitude of the output voltage compares to the amplitude of the applied sinusoid. Okay, and you're going to look at what's called here an attenuation ratio. What that basically means is the ratio of the peak-to-peak amplitude of the output voltage to the peak-to-peak amplitude of the input voltage. Okay, so that's attenuation ratio. Now, quick point of clarification here in question 6 and 7. The lab manual asks you to sweep the frequency from function generator. What it actually means is to step the frequency manually, right? So there's features in the 82 and other function generators that allows you to sweep the frequency really fast from one frequency to the other. But that's not going to be helpful to you as you can't see the behavior of the circuit at each individual frequency point. So what you really need to do is set a frequency to some value, measure the attenuation ratio, right? The peak to peak of the input and output and calculate the attenuation ratio, change the frequency to something different, and then keep doing that for at least 10 frequencies between the range 1 Hertz and 1 kilohertz. Okay. And step 7 again, you're exploring the behavior of this capacitive divider with DC signals, and the manual tells you to sweep the voltage from 0 to 5 volts, but what you actually want to do is step the voltage manually from 0 to 5 volts and get at least 10 voltage levels between 0 and 5 volts. And each time you observe the output DC voltage compared to what the input DC voltage is, and look at whether or not this capacitive voltage divider still acts as a voltage divider for DC signals. Okay, so that is all of the tasks for this lab. Folks who don't have an 82 yet, you're gonna still do the LT-SPICE version of the lab, but it is exactly the same as the 82 version of the lab. The only thing I would say is on LT-SPICE, it's very easy to measure the current through any component, right? As opposed to using an 82, you have to measure the voltage and then extract the current through a sense resistor. On an LT-SPICE, you can directly measure the current, but I don't want you to do that. I want you to get a sense of how to do the same measurements and exercise of measuring the voltage and calculating the current from it even though you don't have an 82, right? So the instructions in the LT-SPICE version of the tasks tell you specifically to measure the voltage across the resistor and calculate the current. So just do that and don't take the shortcut route of directly measuring the current. If you would like, you can confirm your answer by making measurements, current measurements. But to start off with, just follow the same steps that we would do with an actual circuit and actual equipment. Okay. All right, so that would be all for today. Um, and good luck, and let me know if you have any questions about this lab.